Good afternoon. I'm Dave Kankam, the Center University Affairs Officer. Welcome all of you to this last and final presentation on our speaker series. Our topic today will be the physical sciences and biomedical technologies in space. And we have three speakers, but I'll just welcome you to the first speaker who will then introduce the others. Our first speaker is Dr. Brian Mortill. He's the Deputy Chief of our Fluid Physics and Transport Processes branch. He's also the past co-chair for NASA Office of Chief Technologist Thermal Management Roadmap Team. Dr. Mortill has a number of achievements within his career at NASA Glenn. Among those are the NASA Exceptional Achievement Medal, which he won in 2011, the Distinguished Service Medal, which was 2007, followed by prior to that, the Exceptional Achievement Medal in 2003. Dr. Mortill received his BS in Chemical Engineering from Cleveland State University. Subsequently, his Master's in Mechanical Engineering from University of Toledo, as well as Master's in Mechanical Engineering and PhD in Aerospace Engineering from the Case Western Reserve University. It's my pleasure now to welcome Dr. Mortill to make his first presentation to us. Thank you.
Okay, thank you, David. So we're going to start our session out with about a 10 or 11 minute video which gives a historical perspective of microgravity research at NASA Glenn Research Center. And then I will then come in and focus on the fluid physics part of it, and our two other speakers will talk about combustion and our life sciences research. So let's start with the video. In 1957, the same year that Sputnik 1 orbited our planet, ushering in the race to space between the two superpowers, Robert Siegel at NASA Lewis, now Glenn Research Center, conceived a drop tower experiment to study for the first time how fluids would behave in space. His experiment exposed the full effect of a force often masked by gravity but critical to designing spacecraft: surface tension, or capillary force. Interestingly, one of his main conclusions, published in 1961, was proven incorrect decades later, but I'll come back to that. Recognizing how important it was to understand the behavior of fluids in space, NASA Lewis investigators quickly designed the first fluid space experiment, and within 5 years, Commander Scott Carpenter flew it on a Mercury mission to observe how a fluid would reposition in a baffled tank. After that, things really took off for microgravity research in Cleveland. We converted this 100-foot high fuel distillation facility into a 2.2-second drop tower, which is about the longest an experiment can free fall in air before the drag slows the acceleration. Even then, we need to use a drag shield to minimize these effects. The 2.2-second drop tower was considered the gateway to space for many of the early microgravity experiments conducted on the Space Shuttle and even International Space Station, because many ideas were first explored and tested here. Not long after that, construction began on an underground 5.2-second drop tower called the Zero-G facility. By 1966, this premier facility, the largest of its kind in the world, was, and still is, operational. The experiment falls for 430 feet, or about the height of the terminal tower downtown, through a 20-foot diameter vacuum tube to eliminate drag. Traveling over 100 miles per hour, the 2,500-pound package is stopped in about 15 feet by expanded polystyrene beads. In the 1980s, a division was formed at our center dedicated to conducting experiments in the microgravity environment, and we began operating a Learjet to allow researchers to fly along with their experiments while experiencing 20 seconds of low gravity during a parabolic trajectory. We also flew our first experiment on the space shuttle, which was piloted by our current administrator, Charlie Bolden. By the 1990s, we were in our heyday, building a telescience support center to provide around-the-clock operation support for all of our spacecraft experiments. We also refurbished a DC-9 aircraft to handle the high volume of experiments preparing for spaceflight. Today, NASA Glenn operates the fluids and combustion facility on the space station, and we collect all of the accelerometer data to characterize the microgravity environment. We manage all NASA experiments in combustion, fluid physics, and complex fluids, and we have conducted over 150 experiments on the Space Shuttle, Russian Mir, and sounding rockets, and almost 50 experiments have been completed to date on the space station. So let's take a brief look at a few of our recent experiments. The United States alone consumes almost 20 million barrels per day of liquid fuel. Droplet experiments provide an idealized geometry or textbook case to study the chemical kinetics of liquid fuels. However, prior to the Flame Extinguishment Experiment, or FLEX, first flown in 2009, we lacked the important experimental data to fully benchmark the leading theories and models used for combustor design and simulation. This is because it is not possible to maintain the perfect droplet shape throughout a burn under the influence of gravity. Here you see a droplet suspended between two needles with the igniter rings on either side. Once ignited, the experiment proceeded as expected, burning until extinction. Well, maybe. As the process quickly cooled, you see a vapor fuel cloud forming, and then suddenly, what just happened? It took nearly a year for the scientists to convince themselves what they just saw was long considered impossible. What they observed was the droplet continued to burn, but at a very cool temperature, about half the temperature of the hot flame, and then it reignited back to a hot flame to consume the remaining fuel. This low temperature chemistry is known to cause engine knock and limits efficiency, but only lasts for a fraction of a second and is very difficult to observe on Earth. Engine design is like stand-up comedy. Timing is everything. An efficient engine requires the exact chemistry at precisely the right time. The results of this experiment are being factored into important new auto-ignition concept engines which promise significant fuel and emissions improvements. In 2012, this work, now called Cool Flames, won the top discovery award for ISS research. The second experiment I would like to highlight involves some very basic research on liquid crystal materials. Liquid crystals were discovered long ago in 1888 as a material that exhibited properties somewhere between a solid and a liquid state. It took over 40 years before conclusive experiments validated the theory, and then nearly another 40 years before the technology innovations started to impact our daily lives. Today, the LC world market is over $150 billion per year, with new uses and developments discovered on an ongoing basis. The observation and analysis of Smectic Islands in Space, or OASIS experiment, was installed by cosmonaut Gennady Padalka on the ISS this summer and is just now completing operations as the first to study how the complex interfaces in liquid crystals evolve when freely suspended. This video shows one of the exciting ongoing studies. On your left is a full view of a thin film bubble with liquid crystal islands floating around. The right is a close-up view. Over time, we observe how the crystals converge and coarsen under specific controlled conditions never observed on this scale before. This is critical to our understanding how small defects can form and grow, still a significant challenge for the LCD displays. Small improvements in materials or reductions in defects can translate to significant cost savings for the industry. As I mentioned earlier, the very first microgravity experiment looked at how fluids behave in space. Without the strong masking effects of gravity, capillary forces can be dominant and often lead to strange fluid behavior not seen on Earth. Controlling fluids in space is important to life support, propulsion, and thermal control systems. The capillary flow experiment, or CFE, has been one of our longest running and most successful experiments to date, operated by many astronauts as a series of studies on how geometries affect capillary flows. Here's an example of a perforated vein that can be used to wick the fluid up or down simply by changing the gap between the vein and the wall. For example, this is very important for positioning the last remaining fuel in a tank prior to firing engines, as shown in this simulation. Another significant challenge encountered in space is separating bubbles from a liquid which plagues many of our systems. However, through proper use and understanding of capillary forces, separation is really not that hard. So back to Robert Siegel's incorrect conclusion about capillary flows. Siegel concluded that capillary rise in a tube would not auto-eject the liquid from the end of the tube. Here we have reproduced his experiment with a straight tube, and we can see how he came to this conclusion. However, when a nozzle shape is used at the end of the tube, the results are very different. In fact, we can even control and predict the ejection by changing the geometry. NASA Glenn's microgravity research program has produced many exciting results over the years, with much more to come. We have published in the most prestigious journals and incorporated findings into solutions for both Earth-based applications as well as spacecraft designs. In fact, we have even broadened our scope of application to issues such as astronaut health and fitness. For example, our work has led to improving exercise equipment, the types of exercise, and how it affects different physiological systems in space. In particular, the resistive exercise shown here contributes to our research in the effects of the redistribution of cerebral spinal fluid, as well as in bone and muscle loss. NASA has also undertaken 2 initiatives to make this valuable resources available to everyone. In 2011, NASA selected CASES, the nonprofit center for the advancement of science in space, to manage the International Space Station National Laboratory. CASES provides seed money to help fund promising research projects for private industry, as well as direct access to launch and operate possibly your experiment on the space station. In addition, you can go to our new informatics website to access data from past and current experiments. Our hope is that many new insights will result from this database for many years to come, even after NASA moves beyond the space station era. I would like to thank those who helped contribute to this presentation, and I'd like to thank you for your interest in microgravity research.
Okay, so that's our kind of the history of microgravity research here at our center. And now we're going to kind of dive into each of those areas with a little more depth. Before I start, though, I want to remind you that you can ask questions. You can submit questions through this Gmail account shown at the bottom of this screen. We'll entertain questions at the end of each segment, and then again at the very end if there's anything you want to follow up with. Okay? So, we're going to start with the area that I work in, which is fluid physics and complex fluids. Okay. In the area of fluids, we break this up into two disciplines: fluid physics and complex fluids. In short, fluid physics are essentially Newtonian type fluids and flows, and complex fluids are non-Newtonian. And for those who aren't familiar with that term, a Newtonian fluid is simply a fluid that provides a linear response. When you apply a shear force on it, there's a linear response to the fluid. You can think in terms of if you took a cup of water and poured it down an inclined plate, the fluid would flatten out. That's a Newtonian fluid. It would flatten out and flow in a linear fashion down the plate. If you tried that with, say, honey or ketchup or paint, you would get a much different flow field, and those are all complex fluids. In my presentation today, I'm going to focus pretty much on the fluid physics side of this. We're going to talk each of the four areas listed there. On complex fluids, I'm just going to touch on liquid crystals, but I do want you to know that we do also conduct, we have ongoing research in the other areas: colloids, foams, and granular flows. So the overguiding principle for fluid physics is really to enable human exploration in space. So what we're trying to do in this program, in all of our research, is essentially develop this a database so that design engineers, when they go and build the next generation spacecraft, they know how to select what we call the optimum fluid system for the relevant environment. And by that I mean it could be in space, which is normally zero gravity, or partial on a moon or Mars surface. This database that we're developing really helps us develop these very complex CFD models, complex fluid dynamics models, that they then can use and use those to design the next new technologies. And I show some of the areas that specifically relate to fluids. So we break these up into four categories. These are all multi-phase systems. In other words, there's a gas, at least a gas and a liquid phase, sometimes a solid phase. And we break them up into systems with heat transfer and without heat transfer. Without heat transfer, we have adiabatic two-phase flows, which are essentially a gas-liquid flow with no heat transfer. And then very closely related to that are flows that are driven by surface tension or capillary flows. Capillary forces are present even on Earth, but they're often masked by the gravity, which is a much stronger force. On the other side, with heat transfer, we're doing a lot of research in boiling condensation systems, which are done, we typically think of these in the room temperature to maybe a few hundred degrees Fahrenheit temperature range. And then we also focus on cryogenic systems, primarily propellant systems, which are very cold, on the order close to absolute zero. Okay, so in adiabatic two-phase flows, I'm going to show you three very simple examples of how these behave. First, in normal gravity, under certain conditions, we get what we call the slug flow, where you see this gas slug coming through, followed by a trail of bubbles, and it's stratified. The gas is near the top of the tube, liquid is on the bottom. Now, if we go down to the lunar gravity, you see that the stratification starts to go away. These bubbles are more or less centered, not quite. There's still some stratification. And lunar gravity is about 1/6 that of what we see on Earth. Finally, when we go to microgravity, there's no stratification, there's no gravity forces, so the gas goes to the core, and we get a different type of flow field. The bubbles become longer, elongated, and it's fair to say, so what's the big deal? Why do we care about this? Well, it turns out that this sort of slight change in positioning of each phase profoundly affects things like pressure drop, separation, chemical reactors, water processors, and even how to deliver water to plants. In capillary flows, you saw this in the intro video, go ahead, where just by changing the gap between the plate in the middle, which is kind of transparent, and the wall of the cylinder, we can manipulate the fluid up or down. And this is very important to us to be able to manipulate fluids like this in space. Our next video, this is an older experiment from the 90s. It's a drop physics model. These were ping pong ball sized droplets which were that had a surfactant on there, introduced on them, and we acoustically manipulate these bubbles, basically disturb them, get them vibrating like that, and then see how they respond with different surfactants. This research provided insights into things as far-reaching as how stars explode and how nuclei in atoms with extremely elongated shapes respond. They're called hyperdeformed atoms. And then finally on the bottom, this is sort of one of the cool applications that's come out of this research is we now have a coffee cup in space. By simply designing a particular shape with pinning edges, you can see the astronaut filling this liquid in this coffee cup, and the liquid will stay there until the astronaut's ready to drink the coffee. And all they need to do is provide a little bit of suction over the mouthpiece, and they can draw the fluid off. This really made a lot of astronauts happy because it's not fun drinking coffee out of a straw. You don't get the aroma and the smell that you do from a cup. So they're using those on a regular basis now in space. So some of the other applications that come out of this research, of course, the coffee cup. There are microfluidics, which have applications for systems on the ground. There's on the lower right, there are some passive separation systems, which are very important for, say, separating small bubbles that are formed in water containers in space. And then finally, in the upper right, we're using this research to develop better techniques to redistribute fluid in large fuel tanks for rockets, as I mentioned in the initial introduction video. For boiling condensation, on our first video, I want to show the difference between a normal gravity and a microgravity boiling. You'll see on Earth, the bubble, once it starts boiling, the bubbles quickly rise to the top of the container. However, in space or microgravity, the bubble stays there. This gives you a very, very different heat transfer, much less heat transfer in space than in normal gravity. On the other side of this is condensation, and here we show a tube that's being cooled, and there's gas flowing from left to right. And the condensation, you can see the film is very consistent. It's the droplets fall off the bottom. But it's a consistent film and consistent heat transfer. This is something that you would see inside, say, your air conditioner. However, when you go to microgravity, we get a much thicker film. The droplets don't fall off to a certain location. They just sort of break loose and into the gas stream. Again, very different heat transfer properties in space. In the final video, this is a recent experiment where you can see this is a pool boiling, and the little squares on the bottom, the blue color, are cooler squares, so you see less heat transfer, the blue squares. And then right about now, we switch over we begin to add gravity. We get to a little over 1 gravity, and you can see that you get a much better heat transfer or heat flux as all the squares start to turn green, and eventually they turn to red. There's a lot of applications for boiling and condensation, primarily in thermal control systems. A lot of spacecraft today use single-phase systems, which aren't as efficient. But as we go to nuclear power and nuclear propulsion systems, we'll have no choice. We're going to have to go with two-phase flow thermal control systems. So the final area in fluid physics is cryogenic storage and handling. The big issue here is being able to store cryogenic propellants in microgravity without any heat leaks. And we'll go ahead and start the simulation. If we have really small heat leaks, we tend to, the cold cryogen will boil and we'll get a pressure rise in the tank. And over time we have to vent these tanks. And it's such a, our current state of the art today, it's estimated that a mission to Mars, we would have to take about 3 times as much propellant as we would actually use just to account for this boil off. So what you see here is a simulation of a cool jet and this is a technique to redistribute the heat load within this tank. It's impinging on the gray gas bubble at the top, and this model, this simulation is showing how the heat transfers throughout the fluid. And we're actually getting ready to fly the experiment to confirm this model later this month. And I think I've already touched on, the cryogenic propellant is just critical to, it's the most efficient propellant. It's essential to getting to, especially manned missions where we're taking much more mass, to getting to planetary systems. So we really have to understand, how to reduce or even eliminate boil off. Finally, I said I would just touch on one of the complex fluids areas. We already saw this in the intro video, but this is the OASIS, or Observation Analysis of Smectic Islands in Space experiment. And this is what we're doing here is we can study liquid crystals on a scale much larger than anything we can on the Earth. We don't have the sagging effects on the thin film where we're growing the crystals that you do on Earth. And if you want to go ahead and click on that, this is just one of many interesting things we saw where at this dislocation between films, we knew that these droplets were coalescing and merging, but here for the first time we were able to observe that. And that concludes my talk. So I'll pause for some questions. Okay. So I'd like to introduce Dr. Dan Dietrich to talk about combustion research.
Okay, thank you, Brian. As I said, my name's Dan Dietrich. I'm in the microgravity combustion science branch here at NASA Glenn. And I'd like to talk to you a little bit about sort of the motivation and what we do and why we do it in microgravity combustion science. And I think you saw some of that in the nice overview that Brian had before his talk. So if we could put up my slides. Go back to the first slide. Okay. So there's 2 primary motivations about why we do study combustion in space. And I'm going to touch a little bit on both of them. But everybody's familiar with the concept that hot air rises. And if you look, and it's hard to see on this view graph, but if you look at the image here, we have a candle flame in normal gravity, and that's exactly what you'd expect to see if you lit a candle in your room right now. And then we have the identical candle and what it looks like when it's burning in space. And the buoyancy-induced flow in normal gravity is about 1 meter per second. In microgravity, the buoyancy-induced flow disappears, and the oxygen transport to the flame and the combustion product transport away from the flame is all determined by diffusion. And the diffusion velocities are on the order of about a centimeter per second. So you can see there's a vast difference in energy and species transport to and from the flame. And that has a significant impact on what the flame looks like and how it burns. And so a major motivation for our work in microgravity combustion science is to study fundamental combustion phenomena. And this is essentially looking at textbook combustion problems. Now, if you look at any textbook in combustion, virtually all of those sort of classical problems ignore the influence of buoyancy because it so greatly complicates the problem. But in microgravity, we have the ability to study these fundamental combustion problems. And I'm going to give you an example of one next. And just to sort of, highlight that is the sort of quote at the bottom from one of the leading experts in combustion is that the effects of buoyancy are so ubiquitous that we tend to not appreciate the enormous negative impact that it's had on really the rational development of combustion science. And that's just every combustion experiment you do in a terrestrial laboratory has this overwhelming buoyancy-induced flow because combustion always involves large temperature differences, which in turn leads to large buoyancy-induced flows. The second motivation behind what we do is spacecraft fire safety. And you can see just by looking at this candle how vastly different flames behave in microgravity compared to the normal gravity environment. Now, the one thing that this image of the candle on the right in microgravity doesn't really convey is how dim that flame is. Now, if you were to look at that in a dark room, it would be barely visible to the naked eye. So we break up our spacecraft fire safety work. We look at both fire prevention, fire detection, and fire suppression. And all of them are impacted by gravity. And so in the sort of second part of the talk, I'll give you provide a little background on spacecraft fire safety. So if we go to the next slide. So one of the, this was touched on by Brian in his introductory video, we have a large-scale combustion experiment on the space station. It sits inside the combustion integrated rack. It's a 90-liter combustion chamber that has a lot of hardware to change the atmosphere inside the chamber, a number of camera systems that allow us to visualize the phenomena inside. It's been operational on the space station since 2009. And it will eventually house a number of different combustion experiments. The first combustion experiment was a droplet combustion experiment, and this is the textbook problem of a spherical droplet floating in space surrounded by a spherical flame, and virtually every textbook in combustion talks about the solution to this problem, and these experiments really provide one of the best ways to sort of realize this this experimental configuration. But a sort of funny thing happened as we began studying these the droplet combustion experiment. And if we go to the next slide, there's going to be a video here. Not quite yet. But I have the droplet diameter squared as a function of time and then the flame diameter. And so what you're going to see in the two videos is you're going to see a droplet that gets deployed. And because this is microgravity, the droplet will just float and then just drift a little bit because of the residual motion. It gets ignited by two igniters that then pull away. And as expected, this droplet burns with a nice spherical hot flame for a period of time before the hot flame extinguishes. And the primary motivation behind these experiments was to look at that extinction process. But then sort of the unexpected happened, and that is that the droplet continued to burn. And you can see, and if we play the video now, okay. Okay, I can just talk through this one then. Okay, so what you expect to see was when the droplet burns with a hot flame is the droplet diameter squared will decrease linearly with time. And then as the flame goes out, the vaporization stops because the source for the droplet vaporizing is gone, that being the hot flame. Okay, so here we got the video playing. You can see the two views. We measure the droplet diameter from the video on the video image on the right-hand side. Then you'll see that the flame briefly oscillates and then extinguishes, but then what we ended up observing is that the vaporization rate of the fuel, the rate at which the droplet diameter squared decreases, didn't change at all. And it continued in a linear fashion, almost unchanged, until you'll see at the end it abruptly ended. Now, this was a puzzle to almost everyone who observed it, and we finally, as was noted in the introduction, it took about a year to try and understand what was really happening, and it turns out what is happening is right now the hot flame gives way to a lower temperature flame that's a cool flame that burns at about half the temperature, and that cool flame will then burn and extinguish suddenly at the end, and that corresponds with the appearance of a large vapor cloud. And again, this is important because low temperature chemistry is very important in internal combustion engines. It is one of the factors that limits ultimately limits the efficiency of the engine. And so this is of not only significant fundamental interest because it's something completely unexpected, but also of great practical importance. And so we'll move to the next slide and talk a little bit about spacecraft fire safety, and that is all fire safety practices are based on terrestrial fire safety standards, but there are a number of false assumptions regarding fire behavior in microgravity. First, one that we ultimately proved wrong with the candle experiment was that a steady fire cannot burn in a quiescent microgravity. It turns out it can. So simply saying that a long-term fire can exist in microgravity is wrong. The second sort of false assumption is that terrestrial fire behavior represents a worst-case scenario. It doesn't. Fires can burn to lower oxygen concentrations, and they can actually burn at higher rates, higher burning rates at flow velocities that are on the order of the typical flow velocities you find in spacecraft ventilation systems. So as far as spacecraft fire safety, material fire flammability limits change, fire signatures change. So what a detector looks for when it sees a fire has to change, and fire suppression can be more challenging. Water doesn't settle to the bottom. In addition, a spacecraft is a very challenging environment because simply, leaving the spacecraft like you would your house isn't an option in many cases. So one of the motivations is the motivation behind our fire safety program, but it's essentially that the fire safety practices aboard spacecraft should be based on the unique hazards that are associated with fires, how fires burn in reduced gravity. So if we go to the next slide, one of the, and we go to the second video. Yes. Oh. Yep. Are they able to hear that? Oh, I think you switched to me, but with this video is a large-scale fire safety experiment that's being conducted
on Cygnus until all the supplies are offloaded by the crew of astronauts.
on the space station.
Once its supplies are offloaded and replaced with trash from the ISS, Cygnus will depart. Once reaching a safe distance from the station, NASA Glenn engineers working from Orbital's Mission Control Center in Dulles, Virginia, will remotely turn on the experiment. Cygnus will then be put into free drift, while the Sapphire experiment is conducted up to 2½ hours. The experiment's sensors and video cameras are designed to capture valuable data and imagery, documenting large-scale flame spread and material flammability limits. At the conclusion of the Sapphire experiment, the Cygnus vehicle will remain in orbit, while the data captured is downlinked to several ground stations around the globe and transferred to NASA Glenn's scientists and engineers in Cleveland. When downlink is complete, Cygnus will then begin its re-entry through the Earth's atmosphere, where it will burn up over the Pacific Ocean.
Okay, and the unique thing about this is a large scale, unlike a lot of our experiments, this is a large scale fire safety experiment. So these samples are approximately 1½ foot by 3 foot, large paper samples. So they represent large fires. And we can look at how a large fire impacts the vehicle and how it will behave in microgravity. So if we can go back to the slides. And then we'll go back to the last one. And for my last slide, I will show the last video, which is just a brief video of the result of the Sapphire experiment. So this is a large scale, about a 1½ foot by 3½ foot sample. It gets ignited, and there's a flow over the sample. And what you can see is what we're observing now is how the flame spreads in reduced gravity with a ventilation, with a flow that's typical of spacecraft ventilation systems over this cloth sample. And the light that you see flashing on and off is so that we can observe both the flame and the paper, the char front on the paper. So right now we're in the process of data analysis on this, and again, the goal of this work is to try and understand how large fires behave in spacecraft. And so that's kind of a brief overview of our microgravity combustion science program. I'm going to hand it over now to Dr. Emily Nelson, who's going to talk about our human research.
Thank you. Thank you, Dan. So next I'm going to talk about another area that we work on here. It's in comparison to the work that you've seen on the fluid physics and combustion. This is a relatively new area. It's not exactly an infant, but maybe it's a toddler in its terrible twos at this point. And that is the behavior of the human body in space flight. So if we could go to the slides, please. To remind you, you can submit a question to the website that's listed below that Gmail account. And you can ask questions about this presentation as I'm going through it. You can also ask questions about the 2 previous presentations or the movie if you want to as well. So here at NASA Glenn Research Center, we have a human research program because we would like to be able to go beyond low Earth orbit. We'd like to get people out into far space, go to Mars, to the moon, to someplace far beyond Earth orbit. This requires us to have a program that has basic, applied, and operational research so that we can look at things like human health and performance and habitability standards. One of the things about spaceflight that we know is that it's a risky business. So we would like to know what happens to the human body in spaceflight. This is something that's a challenge because we really haven't had all that many people go up into space and have space work its effect on the human body. So we have to come up with new techniques like computational methods or microgravity analogs that we can do on the ground that kind of approximate the microgravity environment and the human response to it. And then we want to look at countermeasures in order to look at things that we're concerned about, things like bone loss, for example. We also look at advanced habitability and medical support technologies, because if astronauts are going to be going to Mars, they're not going to be able to run down to the drugstore to get some aspirin. They'll have to be able to carry everything with them. They'll have to be able to diagnose medical conditions as they arise and treat them. So, in order to do this, we start from looking at an evidence base. What do we know about the medical condition of interest that we're looking at? And go through a series of steps that sequentially identify what are the hazards of this particular condition that we're concerned about, whether we're looking at visual impairment or muscular atrophy or bone loss. Then we look at what do we not know about these different physiological processes, and actually there's quite a bit that we don't know, but we need to figure out what are the most important things that we don't know and figure out how to design experiments or interpret data so that we can get the information we need to fill those gaps. And that comes into the tasks part of it, which really delves into the, all of the little details, and then goes to deliverables. There we go. And this program comes out of the Program Science and Management Office. Here you see that office is separated out into 5 different elements, and the text in blue indicates areas where we have a great deal of work going on here at Glenn Research Center. So the things that we're primarily looking at are human health and countermeasures, things like physiology and immunology, functional performance. The second area is human factors and behavioral performance, looking at the interfaces between humans and their vehicles or habitats or environments. Effects of interpersonal relationships, sleep and stress, and how that affects. It's a challenge to be living in a small tin can with a few different people for many months at a time. And then the last area is exploration medical capability. So if a crew member gets sick, we need to be able to understand what's happening to them. So we need to have some diagnostic capabilities. We need to be able to interpret that information. And we kind of need to know what we're looking for, because, again, we don't have much of a supply chain if we're going to be going to Mars, and we need to be able to predict the sort of medical conditions that we'll need to be able to get data on in order to diagnose and assign treatment for different conditions. So as I said, this is something that really grew out of our engineering background in transport, which Brian and Dan have already talked about. One of the things that's been very powerful is the use of computational modeling for assessing the effects of spaceflight on the human body. And if I can get that to move forward, okay. So there are other groups at other centers who are more concerned with the biology and physiology in the classical sense. But we're really more interested in the technology development, in understanding the cause and effect scenarios that drive the conditions that are of interest, and trying to manage those risks through countermeasures. For example, some of the key concerns medically for an astronaut in long-duration flight are radiation damage, visual impairment, and accompanying changes in the ocular anatomical structure. Also things like bone loss, muscle atrophy, and kidney stone formation. There's an increased propensity for kidney stones in space. So this is separated out. All of these things are kind of embedded in these areas that are highlighted in the dashes here. We've got advanced exercise concepts so that we're able to design equipment and exercise protocols that allow you to be able to have the same kind of gravitational loading that you would have on Earth, except this time we're giving that kind of loading through advanced exercise concepts. We also are looking at technology development for biomedical technology for diagnosis and treatment. Computational modeling becomes very important because since we have such a small experience base of people up there, one of the only ways of being able to get some comprehensive data about human physiology is by using computational modeling. There's also work that's done in terms of making sure that we do those computational models in a very rigorous manner. And then finally, there's always the matter of risk management. So let's talk about that in a little more depth. I realize that you can't see a lot of this, and I apologize for that. But this just gives you a sense of the scope of what we're doing. There are a lot of different things going on. And some of the things that you can see there is different sorts of exercise equipment. And when we design for a spacecraft that's going to Mars, there's not a whole lot of volume to work with. So we have to come up with strategies for loading the human body using very minimal resources. You can look on the upper right, you see a series of images on harnesses that Glenn has developed. That when astronauts run on a treadmill, they don't stay attached to the treadmill unless they're tethered to it. So, and that has not been terribly comfortable. So one of the things that we have done is look at harness design and improve that. We also have to do things like, in order to test different designs and test protocols, we would like to be able to do some ground-based simulation and not always have to use astronaut time for this. So one way of doing that is to place a person on their back, have a treadmill that goes vertical rather than horizontal. The person is suspended so that it's almost like they're standing up sideways. And then the treadmill commences, and then they run, and we can test what kind of ground force reaction forces and other things are going on to try to best mimic what we typically see on Earth. To the left, there are also some things that the entire medical kit that we bring is about the size of a shoebox for going to Mars. So we don't have a lot of space for excess. So in the middle, there's this device called Our Health, which we are developing to be able to analyze blood from a very small volume, just a drop of blood, and to be able to do many, many blood tests from it, looking at white blood cell counts and other interesting blood tests that are not necessarily garden variety, but are associated with some of the medical concerns, like bone loss, that are of concern in space. One of the things that's interesting about human response to space is that there are things that you can see very quickly, and there are things that take a long time to develop. For example, when you move into microgravity, almost immediately there's a huge shift of fluid from the lower part of your body toward the upper part. So you know that if you've got a blob of fluid in space, you're going to end up with some kind of a sphere. The fluid wants to distribute itself about the center of mass and in as uniform a way as it can. The human body is mostly made up of water, so we're no different. So the body configuration is very different. You lose about 1 liter of volume per leg when you go into microgravity, and that moves upward towards the upper body and the head. So they get these skinny chicken legs and great big pumpkin heads when they go into space initially. But the body is able to adapt to this, amazingly enough, to this completely alien environment, and manages to you urinate more so that you lose about 10% of your plasma volume, and you decrease the load of fluid within your body so that this pumpkin head becomes not such a major issue anymore. But that process, this fluid shift, has profound impact on the response of the body because it imposes new sets of stresses and strains on the tissues of the body, for example, at the back of the eye, which is thought to be an important contributor to some of the ophthalmic pathologies that we're seeing. So this slide shows you some of the conditions that we're concerned about in terms of programs that we're doing. There is an integrated medical model that's trying to formalize the risk of different sorts of medical conditions occurring over the course of a specified mission. But there's also a lot of other things that we have to do in order to make the transition into living in space more better. So that would include medical consumables tracking. There are different sorts of imaging techniques we use, like flexible ultrasound. We figure out how to develop an oxygen concentrator module for, say, someone has a collapsed lung or requires some oxygen. It's advantageous to be able to concentrate the oxygen that's present in the atmospheric air, the room air, because oxygen on its own is not a great thing to be having in the environment because because it's very combustible. One of the things that's of concern is that kidney stones are more of an issue in spaceflight. And if you see up in the upper left, you see an image of the kidney, kind of shaped like a kidney bean there. And then right beside it, there are a couple of kidney stones. And the upper one is labeled misery because it's quite big and those are uncomfortable to pass through the system. But if you can just imagine the one below, that's kind of agonizing. And one of the things that we would like to understand better is how these crystals develop in space, what the impact of gravity is on their transport through the kidney, and what kind of challenges there may be for astronauts who may face these issues. There may be pharmacological interventions we can do, changes in diet, that will help them avoid these things. But the first thing is to understand, is understand what the process is. Here's some more with the advanced exercise concept. You see a couple of experiments that were on a parabolic flight in which we got about 20 seconds of microgravity interspersed with 1.8 G. And on this, I think this is the last one, this is something that Brian showed in the movie at the very beginning. And these are some of the biomechanical simulations that we do. On the right side, you can see a simulation of a person doing a heel raise. On the lower left, there is a human being that has different markers put on their body so that we can get data on how a human actually responds when they're doing a heel lift, and measure different reaction forces and loading conditions that will allow us to approximate in space the kind of loading conditions they get on the ground. And then I think I'll just move forward with that and call it a day. So if there are any questions out there for me or for Brian or for Dan, I would invite you to call, or sorry, to send your questions, and we'll be standing by.
We have a question about the medical box kit. With only a shoebox to take, how do you decide what goes in the kit?
Yeah, you hit on just about the most difficult question of all. Of course, when you're talking with the medical doctors, most of them will have specialties, and of course, the most important equipment is the one that has to do with their particular specialty. But we can't have it all. We know there are things we can't do in space. We can't do open heart surgery in space. So it's a matter of thinking about what can we do and how useful is that information. If we are able to, for example, do a huge array of cardiac biomarkers through some kind of a portable blood analysis unit, is that valuable? Well, maybe it's something you'd like to do in a hospital, but really it's not so valuable in space, because if a person is exhibiting some of these biomarkers, they're already in trouble. So that's really the focus of a lot of work, and for almost a decade we've been trying to figure out what are the right kinds of tests that we need to be able to do, and how difficult will it be to do them, and how much value do we get out of them. So it's a really good question, and I wish I had an answer for you, but maybe you'll be working on this area sometime and can figure that out.
Okay, I have a question about fire safety. Has there ever been a fire in space? And how big a concern is that?
It is There have certainly there's a lot of there have been quite a few alarms. The space station and the space vehicles have alarms. A lot of them are false alarms, but there have been small fire incidents. Obviously, the Mir fire that involved the oxygen concentrator was a very large fire, and that was a very dangerous situation. And there have been other cases of overheated materials that have smoldered. And what was the second part of the question? I'm sorry.
How serious is it? How big a concern is it?
Certainly for a long duration mission, the real danger of a fire is that it can obviously do some significant damage to the vehicle. A second concern is that there is some talk about going to higher oxygen concentrations and lower pressures in exploration vehicles, and in that case, obviously, you're entering into higher oxygen, which is a more hazardous condition. So depending on the spacecraft environmental conditions, it can be, the concern can become elevated. But there obviously is a concern because of the consequences to the vehicle and the human health.
Okay, one question on the capillary action, and that is, are there limits to the size or the diameter of pipes that you can use?
No, that's the one of the interesting things about going to microgravity is that without having to compete with gravity, that's the only force motivating the fluid. So going to a larger tube, it'll move slower, but it will continue to move up to fairly large sizes.
Okay, and one question about they're intrigued with the kidney stones, and that is, and bone loss, because bone loss is calcium loss, and if you increase or try and mitigate that through diet, does that cause further problems?
Some smart people out in the audience there. Yes, that's a very important question, and that's something that we're very much working on. Certainly, the bone loss is going to lead to an increase in free calcium in the body, and there is an increase in calcium in the urine that comes out of the astronauts, and most crystals are calcium oxalate. So that is one of the reasons that kidney stones are of concern, because you may have you have conditions that are right for it. But also things move through the nephrons, the tubules inside the kidney in a somewhat different manner in microgravity. There's a longer residence time there to allow the crystal to grow bigger. Okay.
Okay,
So-
well, that concludes our webcast, and we thank you very much.
Thank you.
Thank you.
Good job, guys.